welcome to the ternary and binary nomenclature lecture. I will try to review everything that we've done so that things may become more clear. People are starting to succeed on the quizzes for ternary and binary nomenclature. Let's start from the beginning and see if everyone can become perfect at this kind of nomenclature. The first thing to understand is that it's about neutrality. The final particle must be neutral. An element in the ground state has equal number of protons and electrons, but they're not stable. They're only stable after they react. They're only stable after the individual atom, such as sodium, gives up an electron to be like neon, and it acquires a charge. However, as a part of a larger particle, sodium will combine with possibly chlorine, +1 and -1, to become zero charged, become neutral. So the idea is that a compound, a formula, has to have a neutral charge. It has a positive component written on the left, a negative component written on the right, and then when you combine these two components into a single particle, it has a neutral charge, no charge. Now, there are two types of nomenclature. Binary, where each ion is made of a single element, such as sodium chloride. The name of the positive component is just the name of the element. The name of the negative component is IDE. Chloride, sulfide, carbide, etc. Now, if you have ternary nomenclature, one or both are going to be polyatomic ions. Now, when you indicate the presence of more than one polyatomic ion, because let's say you need 2 ammonium +1 to cancel out the -2 of a single carbonate, you need 2 ammonium. So you have to use parentheses and then a subscript 2 to indicate that you need more than one ammonium. For instance, ammonium pyrophosphate, +1 -4. I need 4 ammonium, so I need to use a parentheses and use 4. Calcium phosphate, same thing. I need 2 phosphate, so I need to use a parentheses. If I use the parentheses and I don't need more than one, for instance, sodium chlorate, then that would be incorrect. Now, what I have here is a chart, and the chart has ions, and then I name the ion, and then I say the number of ions that I want to indicate, and that would be 4. And then I say, okay, what does it look like when I put 4? I use parentheses and a subscript of 4. I have -1 is going to be the charge of each perchlorate, giving a total charge of 4. Okay? Now, what I'm going to do is I'm going to stop this and I'm going to complete this chart. It's going to take maybe 2 seconds for each cell to be uncovered, and then you can go through the entire chart. It'll take seconds. Okay? Stop while you can. Stop while you can, and rewind if you have to. Try to complete the chart with uncovering as few as possible, and see if you're right. Okay, let's begin with the next row. In a moment, I'm going to uncover, and I'm going to start uncovering. It's only going to take 2 seconds for each line. Okay. We obviously know that that's phosphate. 3 ions. Now see if you can write everything else. I'll let this run. I won't talk anymore until it's almost finished. Good luck. Remember to pause where you can, complete before the cells are uncovered. Okay, how did you do? All right, let's put it on pause right now. Okay, here's a problem where a student made a common mistake, simple common mistake on a makeup quiz. Well, it was aluminum hypochlorite, and aluminum has a symbol of Al and +3, and hypochlorite is ClO, -1 charge. Now, what the person put on their makeup quiz was AlClO, and the 3, which they meant 3 hypochlorites, but didn't use the parentheses. And this is what you should get. Okay, very instructive. See if you make those kind of mistakes. I'll be right back, and goodbye. The next thing here is I want to show you a quick way of analyzing subscripts. Let's say the positive component is +A and the negative component is -B. Those will make up the corresponding subscripts. The subscript for the positive component will be B, and the subscript for the negative component will be A. And that's exactly what we have here. It's just a quick way of doing it. You just have to keep your wits about you. If it's 4 and 4, it's got to be 1 and 1. Okay, this table has the positive ions on the left and the negative ions up top. And we're going to look at ratios of the charge ratios, +1, -1, +1, -2, etc. And then how does the charge ratio compare to the combination ratio? How does the charge ratio compare to the combination ratio? Just to see if you can make things, work. See how this works. What I'll do is I will put it on 2 seconds a slide, 2 seconds a cell, and when it gets down near the end, we'll talk about it a little bit. Okay? So it's going to be +1, -1. So that first cell, you see there's 3 cells, that's going to be +1, -1 will be the charge ratio. 1 to 1 will be the combination ratio. Okay, you can see that the vertical column on the left is +1, +2, +3, +4. And then up top, -1, -2, -3, -4. We have the charge ratio, the combo ratio, and the lowest terms. So for instance, sodium would be +1 and chlorine -1. This is just how the combinations and charges will result from working on these nomenclature problems. See if this makes sense to you. You can stop as it progresses and see if you can complete the table without the cells being uncovered. Okay, you can see quite clearly, for instance, where you have +2, -2, that's actually the combination ratio has to be in lowest terms, that's 1 to 1. Another one is +4 and -2, so that charge ratio would be +4 and -2, but the combination ratio would be 2 to 1. The next table that I do will illustrate that more completely with actual ions, elements and polyatomic ions. Okay, see how you did. Remember to restart this if you have to. Go back and see if you can do the table yourself, see if it makes sense to you. Where necessary, you have to reduce to lowest form. To lowest form, you have to reduce, to lowest terms, you have to reduce some of the charge ratios. 2 to 2 is 1 to 1, 3 to 3 is 1 to 1, 2 to 4 is 1 to 2, etc. In this particular table, the left column will be the positive ion, and the top row will be the negative ion. In the rest of the table, for instance, sodium and then the two cells next to it will be, you'll have the ratio, the charge ratio, and then the formula will be written in relative to the combination ratio. So I'm automatically going to go from the charge ratio to the combination ratio, and you can just literally see that you are crisscrossing the charges to become the corresponding subscripts for the combination. Where 1 is understood, let's say it's +4 and -2, so it would be 1 to 2, etc., lowest terms. So here I have magnesium, and then I have aluminum. Next I have, wait for it, carbon. Remember, if it's on the left, it's going to be positive ion, and if it's on the right, it's a negative ion. And if it's a negative ion, it wouldn't be carbon, it would be carbide as a negative ion. Up top, we see chlorine or chloride, sulfur, sulfide, phosphorus, and the ion is phosphide. And then the last one will be pyrophosphate, will be an atomic, polyatomic ion, and it will go as pyrophosphate. There's no modification of that. Now, the charge ratio of sodium to chlorine is 1 to 1. So the combination ratio would be 1 to 1. So it would be NaCl. The charge ratio for sodium to sulfide would be 1 to 2. Therefore, the combination ratio would be 2 to 1. It's opposite. 1 to 3 for sodium and phosphide, and it would be 3 to 1 below that. Now, what I'll do is I'll speed this up a little bit and allow you to, if necessary, stop the video and see if you can fill in the chart without uncovering the cells. Okay? Be right back. You'll never know I was gone in a minute. Hello, now here's just 2 seconds per slide. See if you can clear away the confusion and predict what's under each cell before I uncover them. I'll let you work. Remember, you can put it on pause or rewind. Notice the red ones. Notice the red. You have something that has to be reduced to lowest terms, such as magnesium sulfide. It's 2 to 2. That's the charge ratio, so it's 1 to 1. Same thing with carbon sulfide. And then this is where I slow down a little bit and we look at it. So this one is 4 to 4, carbon and pyrophosphate, so it's going to be 1 to 1. Is going to be the combination ratio. Yes, so it's going to be just P2O7 will be the compound. The next group of slides is, I agree, a little weird, but what I'm trying to do is I'm trying to get you to understand that individual element ions such as sodium or chlorine, chloride, sulfide, phosphide, etc., can be thought of as individual particles. So let's make up some elements. Let's make them up. We have a positive ion. It has a positive 1 charge, and it's called, the ion is called oval. Now, I'm going to take oval, and for that to be truly stable, it has to find neutrality in a larger particle. which we're going to call the unit of a compound. So it's going to search for something. It's searching around nature, search, 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 and it's got to come up with a negative ion or a negative group of ions, whereby it's going to be, oh, there's one, oh, there's one, oh, there's one. Look at all these ions that there are. There are plenty of ions out there with all different kinds of charge. There they all are. There's the rectangle, the circle, the triangle, the parallelogram, the hexagon, etc. And now here's two. Here's the oval. The +1 oval has found a -1 rectangle. It's going to exchange the charges for subscripts. And the subscripts, when they're 1 is understood. So you don't need to put the 1 there. And then you have to be able to name it. There it is. There's the oval, 1 oval and 1 rectangle. And now we have to name it. What are you going to name it? Well, you're going to name it oval rectangle. Well, the difference here between what this is, remember this is an analogy, not an equation, is that if it's a single negative ion, single element, it would be IDE, rectangle, rectangide or something. I don't know. But anyway, let's do another example. Now, another example would be a circle called +3, and then a square -2. We're exchanging the charges and coming up with compound circle square. Here's a triangle parallelogram, exchanging the charges for the combination ratio, and triangle parallelogram, etc. So I'll let this run, see if you can figure out what the formula and the name of the formulas are before we quit. It's going to be oval hexagon, and it's going to be oval 2 hexagon. The 1 is understood. That's the name of it, oval hexagon, and that was the formula. Now I have hypochlorite. Look at this. This is a little new, isn't it? I'm actually going to put them as particles, and we're going to rename those particles and see what we can do with them. So magnesium, I have nitride, I have sulfide, and there they are. There are all the particles that I'm going to use to make up the next group of compounds. Okay, here I have the first one, magnesium and hypochlorite. So I'm going to exchange the charges for subscripts. 1 is understood, and it's going to be MClO with a 2 on the outside of the parentheses. Okay, so think of these as well as parenthetical. If you need a parentheses, you need parentheses. Now, it's not an equation, it's just an analogy. So I will expect you to understand the difference between a hexagon and phosphate and the need to use parentheses. So I will be quiet and let this finish up and come back in a minute. So don't forget your parentheses. When you need to represent more than one polyatomic ion, that's the only time you use parentheses. You don't use parentheses to indicate an element ever. You don't use parentheses to indicate the presence of one polyatomic ion ever. Now, the next table is actually something I gave you for homework, and we're actually coming to that. The left column is going to be positive ions, and the top row is going to be the negative ions. And what I simply do is I write the formula in the top cell and the name in the bottom cell. So what I'm going to do is it's just going to be on 1 or 2 seconds per slide, and I'm going to simply do all of the formulas in the top row for ammonium, and then I'm going to go back and name them. Now remember, when you name them, if the polyatomic ion is negative, if the negative component is a polyatomic ion, it's just the name of the polyatomic ion. If the negative component is a single element, such as sulfide or nitride, you use sulfide nitride, the IDE ending. Okay, see what you can do. Try to shut this off and do the table yourself. It'll be good practice. So it's going to go very rapidly now till the end, and I'll come back on the last slide. Okay? Good luck. Okay, so that's the last slide. The next lecture will be on the Roman or stock system. Now, let me just say something about the Roman stock system. It's exactly the same as what we just did. Exactly the same. All the same rules, combination, charges, etc. The only difference is this. You see all the positive components: ammonium, magnesium, aluminum, sodium. The stock system, the positive component, has a multiple number of oxidation numbers, such as iron, +3, +2, copper, +1, +2, molybdenum, +2, +3, +4, +5. So when you're using the D set of elements, we call them the transition elements. They're the D subshell elements. You have to use the Roman numeral system, and that's this. If you're given the formula, you have to work backwards to find the oxidation state of the positive component. The negative component is always known. That's a constant. Oxygen is always -2. So you're working backwards to find the charge of the positive component, and you're using that charge as a Roman numeral to name it. For instance, iron 3 oxide, iron Roman numeral 3 oxide. Iron 2, the Roman numeral 2 oxide, iron 2 oxide. That's iron with a +2 charge. Iron 2 oxide, iron 3 oxide. We'll be back with that lecture in a couple of days. Have fun, enjoy the weekend, and goodbye.